Hello and welcome in to the example video for lesson 12 for Precalculus 1. In this video, we're going to look at just a couple examples because again, once you see how to do a couple, all the rest you do the exact same way. So I know in the feedback I got from you guys, it's like, oh, can you show us a few more examples? And I have been trying to do that, but with these types of problems, it's there. I could show you 10 of these, and it's kind of just a waste of your time because they're all the same after you see the first couple. So, anyways, all right. So for these, let me share the document camera. All right, so we want to find the x-intercept, the y-intercept, the vertical asymptotes, the horizontal asymptotes. We want to sketch and then find the domain and range. So a lot going on here. The first one, r of x is equal to 1 minus 3x over 4x plus 8. So our x-intercept, we do what? We set the numerator, 1 minus 3x, equal to 0. So subtract 1 from both sides. Negative 3x is negative 1. Divide everything by negative 3. X equals positive 1/3. So my x-intercept is 1/3 and y is 0. For the y-intercept, we do what? We set x equal to 0. So 1 minus 3 times 0 over 4 times 0 plus 8. So these cancel out and I get 1 over 8. So my y-intercept is 0 and 1/8. Vertical asymptote, we do what? We set the denominator, 4x plus 8 equal to 0. So 4x equals negative 8, x equals negative 2. And you'll notice that's how all of these I have to format. So x-intercept we format as a point. Y-intercept we format as a point. Vertical asymptote is a line. So we format it as a line. If on an exam, if I ask you what's the vertical asymptote and you tell me negative 2, you're going to get docked points off because negative 2 on a graph tells me nothing. Tell me x equals negative 2, so I know it's a vertical line going through negative 2. Horizontal asymptote. So I'm going to rewrite the numerator as minus 3x plus 1. So I rewrite the function as minus 3x plus 1 over 4x plus 8. The degree, the power in the numerator is 1. The degree in the denominator is 1. So it's what? It's y equals the ratio of these coefficients. So negative 3/4. So now we can sketch this. These are going to be tight confines here, but we'll try it. So the x-intercept is at 1/3 0, so roughly here. The y-intercept is 0 and 1/8, so about here. The vertical asymptote is at x equals negative 2, and we draw an asymptote with these dotted lines. I should have mentioned that in the first video probably, but so we get that dotted line like that, should be straight, so never mind my crooked line. And then horizontal asymptote, y is equal to negative 3/4. So maybe somewhere along here. All right, so now if my graph is going through these 2 points, I know I have to have a curve going like this. Remember, I can't cross the asymptote, so I get that curvy part in the upper right. And then it's like, okay, where's the rest of the graph go? Well, I couldn't have a piece over here in the upper left because then I'd have another x-intercept because it'd be crossing the x-axis. I can't have a piece down here because then I'd have another y-intercept, which would be a big no-no anyways. So the only other position this could have a graph is down here. And if you want, you can even like you could plot a couple points here. So I know that -3 is somewhere over here. So if I plug in -3 into the equation or into the function, I get what? -9 plus 1 is -8. And -12 plus 8 is -4. So -9/4, which is like -2 and something. So down here. So you know that there's a point running here anyways, which is how you can confirm that, okay, I have a graph in that section. So then my domain is what? Well, we know it's everything other than the vertical asymptote, which was -2. So it's -infinity to -2 union -2 to infinity. And the range in this case is everything other than the horizontal asymptote, which is going to be what? Everything other than -3/4. So we have -infinity to -3/4 union -3/4 to infinity. That's what we get for that one. Those are all the different pieces of information we can get from that function to sketch it, to get domain and range. And so the second one, r of x is equal to 6x minus 18 all over x squared minus 5x minus 6. All right, so x-intercept, we do what? Set the numerator, 6x minus 18 equal to 0. So 6x is 18, x is equal to 3. So my x-intercept is at +3, y is 0. Y-intercept, set all the x's equal to 0. So I have 6 times 0 minus 18 over 0 squared minus 5 times 0 minus 6. So all of these guys cancel out. So I get -18 over -6, which is +3. So it's at 0, +3. Vertical asymptote, we do what? We set the denominator, x squared minus 5x minus 6 equal to 0. So this guy will factor into x minus 6, x plus 1. So x equals 6, x equals -1. So I actually have two asymptotes in this situation. And then horizontal asymptote. Well, I look at the degree of this. The degree in the numerator is 1. Degree in denominator is 2. Therefore, the bigger degree is in the denominator. And when that happens, I have a horizontal asymptote at y equals 0. So to sketch this now, so my x-intercept, my x-intercept is at 3, 0. My y-intercept is at 0, 3. Then I have two asymptotes, one at -1. One at +6. And then a horizontal at y equals 0. Excuse me. Man, between the coughs and sneezes, what's going on here? All right, so this graph is going to be a little bit funny looking. And I wanted to illustrate with this problem to show you that horizontal asymptote, so we know that the vertical asymptotes, that we can use that for our domain. But we can't necessarily do the same with our horizontal asymptote because with examples like this, when I graph this middle section is actually going to have this sort of snake-ish shape. And then the end, so you can see this actually goes right through the horizontal asymptote. Because a horizontal asymptote doesn't mean like, oh, well, this thing could never be that y value. It means as we get towards, remember, negative infinity and positive infinity, it won't hit that specific value, or in this case, 0. And so now to determine, because before we could figure out like, oh, well, okay, I guess, the curve is up here, down here, whatever. And so if you want, like, pick a point and try it. Let's see, 6, 7, 8, 9, 10. So let's do 10 if you want. If we plug in 10 into my r of x, I get 6 times 10 is 60 minus 18. And then 10 squared is 100, minus 5 times 10 is 50, minus 6. So I'm not actually going to calculate the values. Instead, I'm looking at what? The numerator is positive. The denominator is positive, meaning I end up with a positive number. So over here, when x is 10, I get a positive number, meaning I'm up here in this part of the graph. So I get this curvy portion here. And if I do the same thing here, let's try -2, right? Because that's after my vertical asymptote here. So if I try -2, r of x, so -2 times 6 is -12 minus 18. And then -2 squared is 4, minus 5 times -2 is plus 10, minus 6. So I get what? A negative number over a positive number, which is negative. So at -2, I'm in the negative zone, which is down here. So this portion of the curve ends up there. So that is actually what the graph looks like of this rational function. And so my domain then is what? Well, my domain is everything other than the vertical asymptotes. So negative infinity to -1, union -1 to 6, union 6 to infinity. But the range is what? Well, because of this middle piece alone, it's everything negative infinity to positive infinity. All real numbers. So that's it. Like I said, we could do 10 of these, but it ain't going to matter because they're all done the exact same way. When you need x-intercept, set the numerator equal to 0. When you need y-intercept, set x equal to 0. When you need the vertical asymptote, set the denominator equal to 0. When you need the horizontal asymptote, use our little rules. Where's the bigger degree? Sketch what you know. Plot a point if you need to define to figure out the remainder of the graph. And then from the graph, you can determine your domain and range. So that's it. Those are the examples for lesson 12. Come on back and we will look at lesson 13.